of embedded space, you could say. A Raspberry Pi 2, you go for the 3 version as well. It's fairly high-powered, like ARM chips, quad cores, 900 megahertz, a lot of RAM actually for a small device, and plenty of flash through external micro SD card support. And it's not that expensive, and it can run just about any operating system, including Windows, and lots of sort of real sort of, you could say, embedded OSs. Like I think Linux is probably the most used ones on these Raspberry Pi devices. But it's really the same kind of OSs that you're used to running on your desktops and on your servers. If you switch it around and go to the microcontrollers, the difference is it's certainly there. It's still running, a lot of them are running ARM CPUs, a little bit less, clocked less aggressively. Usually we see people running at the high end of the embedded space, Cortex M7 chips. Then the amount of RAM is quite limited here, so we probably see around maybe 300K on a very good day. But maybe the biggest difference is really that a lot of these chips do not come with a lot of fancy memory management support. So that means that they cannot really run any of the regular OSs in any meaningful way. Even micro Linux, UC Linux, which is sort of scaled down, not using the MMU and everything, still takes up too much RAM to run in these devices. So it doesn't really fit. So you're sort of stuck in a mode where you don't have an operating system, so you need to run sort of on the bare metal on these devices. This is our focus in the Dartino project. We want to try to make it a lot easier to write software for microcontrollers and maybe sort of bridge the gap a little bit so that some of the things you can do on microprocessor based devices is also possible in a microcontroller space. So I don't know how many people here are familiar with Dart. Show of hands. Oh, it's like a third of the people here know about what it is. So Dart is actually a fairly heavily used language at Google these days. It's mostly used to build web applications. Google AdWords is building the new version of their product in Dart. So it's sort of an unfamiliar territory to venture into to try to make Dart run really well on these small devices. The code is fairly familiar to people with an interest in languages based on curly braces. It looks like C, Java, C++, C#. There's certainly a lot of inspiration from those languages, and it's designed to look very familiar. And I think in many ways that worked pretty well. It also means that it sometimes comes across as a little bit of a boring language. It doesn't feel very novel. It doesn't feel very exciting at the syntax level, but there's a lot of good properties in the language also for making it run on these small devices that I'll try to go through. If you want to try it out in a browser, you can go to the Dartpad site and just play with the language a little bit there to get a feel for what it is. So why would you want to put something like Dart on a microcontroller? There are a number of reasons why. I think one of the most important things is that the number of developers in the world that are actually comfortable and productive writing software for these devices is very low. So it's very hard for people to actually to scale up and build good software for all these devices out there. So it's really important that we make these small platforms accessible to more developers. It's also, I think, important that that this area of software development for these small devices is certainly an area that's still lacking a lot of innovation. It has a very sort of old school feel to it. So I think it's important that we upgrade the development experience and make it much more modern and productive. And we need to turn some of the proprietary stacks into something that's more open and more flexible. So we have a possibility to actually get some innovation going in that space as well. Everything we do in the Dart and Dartino project is open source, and we're trying to seed some technology here and try to make it useful. So in a sense, I think we really need to extend the tool sets that our people are used to building software for these small devices. GCC is already the biggest thing that people use in the space, plus a lot of sort of more hardware near tools. I think we need to extend that a bit and don't have like C code and GCC and GDB be the only options in these devices. It's a very, very scary place for people that just have a good business idea. They want to build some software for embedded devices to venture into, and a lot of people just cannot get it done at all. I used to think that the biggest problem was actually like doing the hardware side, but it seems like software on these small devices is a really big issue too. We talked to a lot of people that are building these small devices, and even in low quantity software, the software side of the of the cost of building new devices is sort of estimated to be maybe 2/3 of the overall thing. So that's certainly changed, right? Even if you look at a 500 to 1,000 quantities of custom hardware design, so which is somewhat surprising. I think that it's already getting there. So I think we need to do better than this, at least for the you could say the higher end of the low end embedded devices. We're specifically not targeting small 8-bit microcontrollers or anything like that. I think there are much better tools for that. But for these fairly spiffy new devices that come out, you can do better. So the programming model that we're proposing for a managed language on these small devices needs to be a little bit more flexible than what you can get from a stack based on C. So what we do is at the bottom layer, we have a traditional embedded real-time OS. We use FreeRTOS for a lot of things because it's open and available, and we like this sort of accessibility that's built into that. On top of that, we put the Dartino runtime, and then we actually allow you to have multiple independently developed programs that run on top of this setup. This is very different from a lot of the systems that run straight on the embedded real-time OS, because they don't really have a way of running sort of independent components in a truly independent way, because they also interfere and needs to be linked together in one sort of ELF file at the end of the day, or one binary file that can be flashed. So this is an area where having a abstraction layer in form of a runtime, a virtual machine you could say, really adds some value that you can get from a runtime instead of having that from a traditional OS based on systems that have memory management support that allows this. On top of these multiple programs, we actually do run multiple processes, so you can have multiple sort of independently executing versions of the program or parts of the program running next to each other. It's very much inspired by some of the success with Erlang, where being able to sort of model your concurrency in a very straightforward way by splitting it up into multiple independently executing processes seems to be a good way to get some more fault tolerance built into your application. That's actually a thing that people writing software for these devices is very interested in. They feel like there are core components that they'd like to make very robust, and there are other parts like the UI that they could probably live with having to like sort of restart if things go bad. But there are certainly things where they communicate with their networks, or they do the upgrade of the firmware that just needs to be very robust. So having the ability to isolate certain components is a very good thing. So to make this actually work on these small devices with a few hundred kilobytes of RAM, the process needs to be very lightweight, like in Erlang. So small memory footprint for them, a few hundred bytes. We also need them to be able to block and wait for some event without taking up a lot of system resources, which means that you cannot just map a process that runs on top of Dartino to a thread or a task from the underlying OS. Those things are simply too heavyweight. So we have to sort of multiplex on top of fewer native threads. And it's a nice design if you can make sure that if you ever end up on an embedded device with multiple cores, you can run these things in parallel. So that also influences our design a bit. Right now, we're actually not running on any devices that have multiple cores, so they don't really run in parallel, but they certainly do execute and in an independent way with preemption and everything. So one of the things that this allows you to do is that when you're building some sort of network-connected device, you can handle new connections and new processes because the overhead is fairly low. And here's an example of this piece of Dart code that runs on these devices, where you just keep accepting incoming connections and spawning off new processes as you do that. And in this new context of a new process, you can do some UTF-8 encoding. Is probably not the heaviest operation in the entire world, but at least you can do this off the side. If you did something here that you were more worried about getting right, something that could compromise the integrity of your system, it probably would make more sense. It's a little bit derived. So it just shows that it's possible to have this sort of more blocking mode where the spawn accept will actually not continue to execute until it gets a new connection, in which case it will then spawn off another process. So to actually get these processes to do anything useful for you, you need them to be able to communicate. Based on some other languages like Go and other systems like that, we've experimented with using channels and ports for that. A channel is a queue of messages, and a port is a it's a sort of a reified object that acts as a capability to send to a certain channel. So without having gotten access to a certain port, you cannot send to the channel that sort of sits in the other end of that port. So there's no way you can invent a reference to a channel, you could say. It allows you to do simple things like this, where you spawn a process and you just keep sending messages from one to the other, and the other process will then just start consuming them from that channel. Very simple stuff. In some ways, you could say this is almost too easy, right? The only thing you saw here was sending integers, which is almost trivial to send between any kind of in any kind of system. So you probably need to be able to send something more structured than just integers and strings. So it's certainly an option just to say, like, why don't we just have like shared state concurrency between these things? We'll just say you can send any object as a message without copying it. So you just like get hold of a reference to the other object. At least that's a very, very cheap way of sending objects around the system like that. Then you can have these multiple processes just sort of operate on these objects potentially in parallel if you end up with multi-cores. At least concurrently in a very uncontrollable way, you could say. And then we just throw in some explicit synchronization primitives to make it all work. How does that sound? Most people don't like it. They don't want that model. So that's not the model we implemented. We have something very similar though. And the only thing I had to add there was the immutable word. So any deeply immutable object can be sent as a message without copying it. So if the runtime can guarantee and can prove that what you're sending cannot be changed after you send it at all, then it's fairly safe for us to share these things, and you can have these multiple processes operate on these objects without any issues. And then there's no need to have explicit synchronization support in the language or on the core libraries, in addition to what you get out of the channels. So this seems like a much better starting point for these things. So either you destructure your mutable objects and send something more primitive, or you are allowed to send without copying objects that are sort of provably at runtime deeply immutable. This is not based on static typing. It's based on dynamic properties of the object. So, and a deeply immutable object is an object that only refers to other deeply immutable objects and that does not have any way of mutating its own state. And it's pretty easy to maintain information about that at runtime. It's also possible, sort of Erlang style, to monitor certain processes and figure out what they're doing if they're misbehaving. So the usual way of spawning processes actually makes the spawner and the spawnee linked, so that if one fails, the other one fails too. But you can sort of opt out of that model by like spawning it in a detached way, and saying that you want to monitor any kind of events that flow out of the process in terms of why it's suddenly terminating or getting killed or getting uncaught exceptions. So you have a way of sort of receiving those events and acting on them either by restarting the process, and again, very much inspired by similar approaches in Erlang and other systems. So you saw here that there is a call to receive that's blocking. So you may have this problem that within one process, you can only really block on one thing at a time. And we found that it's a little bit too limiting, and people want a little bit more than that. So we've experimented with an approach that have a cooperative set of concurrent fibers within one process. They are not preemptively scheduled. They are concurrently executing. They're built on a coroutine model, so they're also sort of coroutines underneath. But it allows you to sort of wrap part of a call that does a blocking call in a new fiber and sort of fork that off and get two sort of threads of execution within one process. Here they do share an address space, so they can share mutable memory in this way. And that's the reason why we prefer not having them preemptively scheduled and get more control to the developer in terms of more easily understandable places where you might do the switch between them. So that's the sort of the fiber model. So I think when building a somewhat dynamic language for these small devices, the biggest issue we run into is how do you do the dynamic dispatching, the call of methods, without wasting too much RAM on these devices, and how do you make that actually work pretty well? I used to work on V8, and the tricks we use in V8 to make it run fast all require us to do like mutations and caches and lots of sort of small adaptive tricks to make it work well. We just don't have that amount of RAM to do this on these devices, so we've had to sort of look in the literature a little bit and find some other ways of doing it. So, like, the fundamental challenge is fairly simple. Like, if you want to call a method on an object and you have no clue on what kind of object you might get at that point in your code, you need some way of finding the right method and invoking it. And finding the method is the one thing I want to go through here. This is sort of the fundamental problem of having a system like this run well and run efficiently. So, like, the most naive approach in a Dart is sort of single inheritance language. The most naive approach to doing this is just look at the class of the instance that you're calling something on at runtime, and then just like traverse the class hierarchy looking for the method, like traversing up the superchains, looking at the method tables in the individual classes. It's a fairly slow process, and there are lots of ways you can make that faster through binary searches and hash tables and whatnot. Like, all the classical tricks apply here, but at the core of it, this is sort of what you need to do, right? If you have an instance of A and you want to find the method foo, you look at the methods in A and you find it there, you're done. But if you look at an instance of B instead, you have to look through like bar and toString before you realize that it's not defined on B, and then you can traverse up the class hierarchy, reach object, and look through the methods up there and realize that it doesn't exist. And it's sort of a simple process, but a little bit too expensive. People have spent a lot of time optimizing this in the past in dynamic systems. So usually where they start is through a sort of a global lookup cache of some sort. And mostly they end up with a system that looks like this. Like, they have two sort of hash tables, like a primary table and a secondary table. And the reason why they have two tables is because when you build these systems, you really want to have the lookup in the first table where you expect to get most of your hits as simple as possible, which means that you don't want to deal with collisions in that table at all. So you have this way of demoting entries where you do hit collisions in the first table to a secondary table to make the cost of collisions smaller. But of course you also might need to then, like, there's only two levels here, and you can add any number of levels here if you want to, but at some point you'll end up throwing information out or having hash tables that actually deal with the collisions. So this is actually what people have done in the past, and it's something I've built myself as well, where you have really trivial hash functions for these two tables. You have different hash tables. In this case, one of the options is to have the hash be, it's like the XOR of the address of the class and the selector. And in the other case, in the secondary table, maybe you flip it around and say you have a similar simple operation like subtraction that also gives you a really cheap to compute hash code. And like, if you look at from a sort of an abstract point of view, like, the kind of code you'd need to go through to actually look up in this table is something like this. Like, first you sort of probe the primary table, see if the entry you find there matches the class and selector you're looking for. If it does, you're done. And this is where you hope to spend most of your time. Like, just hit that table and you're done. If that doesn't work, you look in the secondary one, and if that's there, you're fine still. And otherwise, you have to go through the expensive step on doing some sort of class hierarchy-based lookup, demote the primary to the secondary table, possibly retiring an entry in that table already, and then update the primary, overwrite the primary cache entry with new information so that you might hit it next time. It's really hard to actually make this work really well. Like, it works pretty well if you can get your program to always hit the primary table, but in practice it turns out to be almost impossible with these trivial hash functions. Like, you're torn between having to have really trivial hash functions that are really quick to compute and get through, and also get some very low sort of collision rates. So it's just kind of hard to do. The machine code you want to run and want to hit when you go through this is something like this, right? Where you just XOR the pointer to the receiver class and the pointer to the selector together, and you just mask off some bits to make sure you hit the table, and then you look it up and you compare the entries in there to make sure that you're hitting a valid entry in there. And if this actually works and you're not taking the conditional branch at the end here, then it's actually a pretty fast thing. So it's really the problem with this approach is that you're not always hitting this case. You end up in the miss case quite a lot. And additionally, it uses a fairly significant amounts of mutable memory. Like, the size that we need to run on these small devices, we easily have maybe 4,000 entries in the primary table and a couple of thousand entries in the secondary table, and it really adds up. Like all entries have to be maybe 16 bytes, and it's a bit too much. If you have a multi-threaded system, manipulating this table is also expensive, just because you need to synchronize or have thread-specific versions of them. So it's a complicated version. Like the next level up here is to avoid doing the sort of the global lookup caching and go for inline caching. I don't know how many people here are familiar with the term. A number of people sort of know what it is. It's actually just saying let's associate the cache entries with the call sites instead of having them in a global table. And that means that for any call site, the selector is a fixed thing. Like if we do object.foo, object might vary, but the name foo does not vary. So you don't have to check that when you validate that the cache is correct. And you don't have any hash collisions here. So like the kind of code that you can run through here to make this run fast is kind of neat. Like the original approach for this is to say, like, let's just put in the code, a check for whether or not the class is what we expected it to be, and if it is, then we'll just go ahead and do a direct call to that code, and then we'll use like self-modifying code to just patch this up whenever we end up in the miss case. Self-modifying code is sort of not that hot anymore for security reasons, and on these small devices, you don't have enough RAM to store all your code in the mutable sections anyway, so you do have a problem there. Most systems are sort of going away from this approach, and they are not anymore relying on self-modifying code for doing these things. Certain architectures also come with a fairly big cost to do these things, like where you have to explicitly go flush some instruction caches to make this all work out. So it's back in the day, this was a very clever technique, and it worked really well. Today, it's sort of not the way to go anymore. So most people end up with something like this instead today. It's just another level of indirection. You move the data in the cache outside of the code, makes it easier to patch it up. But it does mean that the direct call you had before now becomes an indirect call through a cache entry object that might have gotten patched up. So here you're now relying on the branch prediction engine of the CPU to do a really good job to get good performance out of this. So in some ways you made it a little bit harder on the underlying system to make this right, but you do get some nice benefits in terms of security that you don't have writable sections of code floating around the system. It still has this problem that it requires multiple words of mutable state per call site. It's hard with the multi-threading as well. And it only really handles like the monomorphic call sites, places where you only see one kind of object floating around. That's the only thing it really handles well. It certainly can be extended to the polymorphic cases, but it doesn't really deal with call sites where there's a large set of different kinds of objects flowing through. It doesn't really deal well with that. You need another approach for that. So like none of these approaches are super attractive on these small devices because you have so little RAM, and it's so hard to control the performance of these things. And we find that for certain benchmarks we can make it run pretty well, but there will always be another benchmark and another program where we will not hit the sort of the sweet spot performance-wise, and you end up having issues there. So having something better to fall back to, or entirely different strategy seems very like a very attractive thing to go for. So if we take a step back and look at sort of the core problem here, you have an object and you want to call a method on it. Like in some systems, right, you actually might have like static type information for everything you do. So you have something like this, like a, and you know the object variable here always refers to something of type A. So if A is a class type and you have single inheritance, you could probably do something much better here and go through like something like vtables, where you just use the fact that you know that at this point in the code you only see A's, so you can compute an offset into a table at compile time and just stuff it in there. That just doesn't really work in a dynamic system, right? Because first of all, A might not be a class type; it could be an interface type, and also you will have code where you don't have type information. So you need to make the general case run fast too. The question is, can we get some of the benefits of vtables without having to go through adding static typing everywhere? And I think the answer is yes. If you take a look at something maybe slightly more complicated, and think of a simple solution here, which is to say, we take all the methods and class in the system, and we create a matrix. And that matrix will be essentially all methods, all combinations of classes and methods in the system, and we just like lay it out there and say, why don't we just say that the classes are A, B, C, and D. We have foo, bar, and bas methods, and you have this table, and you just look up in it, and you find the right method to call, and it's a constant time operation. It's very, very cheap, very simple to do. That seems like an attractive approach, right? Except for the fact that this table will be huge. Like, it's going to be really, really big. Like, the number of method names and the number of classes in any reasonable system is going to be too much for you. But other than that, it feels like it's a kind of a nice approach to it. So why don't we just run with this sort of this model and see if we can actually make this become somewhat smaller. And this is where a technique called selector-based row displacement comes in. Essentially, you see here that there are rows that have lots of empty slots in them. So why don't we find a way of using those empty slots to store information from some of the other rows? So we can actually compute, say, essentially one row where these different selector rows are sort of displaced down on each other. So the row could end up looking like this instead. So you have all the methods that are defined in the system in one table, and you use and reduce basically all the holes, except for a few, in this layout. So how do you go about computing this table? How do you make it work? Well, the trick is to assign an offset to all the selectors, so that the selector offset plus the ID of the class will give you the right entry in this table. So if we want to take, say, the bar selector here and lay that out first because that's the longest one, then you can sort of see that we get to give bar offset 0 to make sure that if you actually call bar on an A, which has index 0, we end up hitting the 0th entry in the combined table. And so forth with all the other possible classes that either have an implementation of or have inherited a method definition for bar. So for the next one, for foo, it's a little bit more complex, right? We need to make sure that the B implementation of foo ends up in entry 4 there, and B has index 1, so the offset for foo needs to be 3 to make this work. So we assign foo the offset 3 and then just put these things in here. You may have noticed that I'm adding some extra numbers next to the entries down there, and that's because now that we started overlaying these entries, we have to make sure that we don't sort of by accident end up grabbing hold of an entry from another row when we call a method there. So when I call, say, foo on an A, I would actually, by adding foo's offset 3 to A's ID 0, hit the third, well, not the third, but the index 3 in the table, which is an implementation of bar. So I need to verify that the entry I find in the table is actually for the right selector I'm looking for. And it's kind of neat to just be able to use the offsets of the methods for the selectors for that. So just verify if you call foo on an A, you'll hit index 3 in this table, and you can verify that offset in that table is 0, not 3, so it's not a valid entry. And then you don't have to go searching for anything. You just need to say this is not a method that exists anywhere in the system, and it's a constant time, sort of no such method invocation again. When you then want to add the last method here, you might run into the problem that bas needs to get an offset that is 4, not 3, and you might get holes in this table. And it's because it's really, really convenient to have the same have the property that you have unique offsets, so this validation becomes a simple comparison. Does it make sense? Just like overlaying, putting them down in one table, and then off you go. It's much simpler than the other approach that we've seen so far. Like you need to grab hold of the class ID from the receiver class. You need to add them with the selector offset. You need to look up at the table, and then you need to validate the entry. But other than that, you're good to go. So except for the fact you have to validate the entry, this is almost like a vtable call. Vtable calls don't have to validate any entry. Here you have to check that the one you find is correct for you. This is a small price to pay, I think. So this is actually what we implemented in Dartino. This is what's running on this device, and I'll show you that in a moment. And it works pretty well. It's guaranteed constant time. Maybe the nicest thing is that the whole table is pre-computed and it's stored in the read-only segment, which is like flash of the device, not RAM. The downside is it takes up a little bit more space than vtables, which is not necessarily the most compact representation in the first place. But we can move all of that to Flash and have like no RAM usage at all, which is kind of convenient. So I think this actually is a good approach if you have closed world assumptions and you have a setup where you want to have really fast dispatch without relying on static types. I did not come up with this strategy at all. It's a well-known technique, documented, I think, in a really nice way in a book by Carol Driesen. And if you're interested in this whole area with dispatching and calling methods and making that fast, I certainly recommend the book. Covers lots of other details as well. And as many other good things in this field, even though it's 15 years ago this was written, it's certainly not dated at all. There's lots of wisdom and truth in there today still. So I want to just end up just showing you some of this stuff on a real device. I brought one with me here, and it might be a little bit hard for you to all see it, but you can always come find me afterwards and you can get a proper demo of how it actually runs. What we built is a small SDK that allows you to run Dart code on Cortex M4s and M7s. This is the M7 device I brought today. It has a nice touchscreen, so it's easy to sort of show how this all fits together and how it all works. We're still pretty early in the process of building this thing, and we're trying to figure out if everything we've sort of put together here fits well and is a useful way of developing this software. But so far, I think it's become very apparent that it's very easy to make it a lot more accessible for developers than the current tools. So I think there's a lot of benefits in actually providing an SDK that's much easier to get going with a high-level managed language. So the way you would run code on a device like this from a command line shows that you can certainly run both this Dartino code on your development machine and on the device. Here, it's not very interesting to see this on a slide, but it just shows you that you can choose to run your stuff on your, in this case, your MacBook, or you can flash it on the device and have it run there. So I actually did a bit of flashing before you guys came here. That came out wrong, but I did update the device, and you can actually see it running here. It prints hello from FreeRTOS on the device, and it works pretty well. If you want to see a little bit more sort of code in action, I built a small app for this thing in Dart using our sort of preliminary tooling for this thing. Right now we're building a small plugin for Atom to get a feel for how this all works out. But this is actually Dart code running that will run on this small device in a short while. It shows you that you can have like a main method, sets up some like channels and ports to communicate. It creates a separate process to actually pull the touch state of the display. So it's touch enabled. If you look at the code for the touch state, pulling, it's down here. This is very much the way people write, say, Python or Arduino code for these small devices, like small loops that ends up sleeping for a while, pulling the underlying state of the system. And in this case, it's a very simple thing. It just pulls the state. If there's nothing pressed, it will send that information to the other process. If there is something pressed, it will check whether or not it's changed enough that we want to send it to the other side, or if we want to filter it out right now. So it's a very, very simple thing where you see like the distance to call down here between these points. The points themselves are immutable objects, so I can send them between the processes quite easily. And they end up here where we're receiving the events and drawing a line between the previous point and the new point. So if I run this, it will actually start, maybe you can see down here. And this is probably the most painful part of working with these devices. The flashing process itself is somewhat slow, something we're looking at doing sort of a more incremental approach to. It takes probably around like 5-6 seconds using sort of standard tools with this flash. And it means that whenever you want to experiment on these things, you have to wait and wait and wait. And I'm still waiting, so it's probably more than 5 seconds if things actually work. It's up and running now. And now some of you might be able to see me touching the screen at least. It's actually drawing stuff here on the screen. You can come play with it, but it's a very simple demo of what you can do here, and it just shows you a proper high-level language running on these small devices. So I think the conclusions are fairly simple, maybe not that ground shaking yet. Like the open software ecosystem for these small embedded devices is still very much in its infancy. Uh, that GCC and GDB has come a long way in this space, and they're much easier to use today than they used to be. ARM is doing a good job in packaging them up and making them available. But it's still kind of hard to get started on these things, and it requires a special kind of programmer to be productive there. It's very clear that the world needs more developers for these devices going forward. Like the amount of software in these devices is going to go up, and we certainly need to be able to equip more folks with the abilities to deliver something good on these devices. And our job here is to try to make embedded software development easier through a managed runtime and language play on these devices. I think that's it. How am I on time?
We have about 2 minutes for questions. We're running
Great.
a little behind in the room.
Why have you picked up Dart and not other language like Go or, for example, ECMAScript?
So it's a very good question, right? What makes Dart so fitting here? I mean, part of it is the language, but it's also very much around the core libraries. I used to work on V8 and JavaScript, and an efficient implementation of JavaScript is much more complicated than an efficient implementation of Dart. So, like getting the runtime system into the kilobyte range, not the megabyte range, is very, very important here. And making JavaScript run fast on these devices would be much, much harder. Go is a very different beast. I think it would be fun to have Go running there as well. I think a lot of people find Go very attractive. I think a lot of people also find simple object-oriented languages fairly attractive in this space. Actually, I think the most popular alternative to C and maybe Java on these devices is Python in the form of MicroPython. So I think there's a lot of interest there. But I mean, Rust, Go, there are certainly other alternatives that would probably do well there as well. So.
One more question. Would you recommend using Dartino for systems that have hard real-time requirements, let's say building musical instruments?
No, I think the short answer is no. Like we're getting really good at interfacing with external code. So if you probably want to keep your hard real-time constrained code in a lower level language, it's very hard for us to guarantee that GC pauses will be predictable enough for you, and it's not an area we're investing in. So short answer is probably no.
The question is about GPIO. So, like, what is the support for GPIO? Is it like a native support? Like, you need to have like library as well microcontroller, or does it need to be something like the communication goes through sysfs or something like that? How do you do that in Dartino?
So there is no sort of sysfs on these devices. So it's much more native. We're building the libraries for a number of these devices, but it's certainly an area where people with a little bit of skill sets into how these devices work, and maybe the way you write the same thing in C, that would be an easy way to contribute to something like this.
Last question.
Final question.
Okay, and how much memory is your runtime actually taking? Like, how much is left for the application itself? And how do you debug in these machines?
So the RAM consumption is mostly for GC metadata. So all the supporting structures we need for keeping our garbage collected heaps around. And I think we have an overhead there of a few percent. So I would say that the RAM overhead is probably in the maybe 20 kilobyte range, and the flash overhead is much more significant. Probably in practice with the free RTOS and all that stuff, 150, 200K. Flash, but we're focusing very much on bringing down the RAM numbers. So, thank you.
Okay, let's thank the speaker. Thank you.
Of embedded space, you could say. A Raspberry Pi 2. You go for the 3 version as well. It's fairly high-powered, like ARM chips, quad cores, 900 megahertz. A lot of RAM actually for a small device, and plenty of flash through external micro SD card support. And it's not that expensive, and it can run just about any operating system, including Windows, and lots of sort of real sort of, you could say, embedded OSs. Like I think Linux is probably the most used ones on these Raspberry Pi devices. But it's really the same kind of OSs that you're used to running on your desktops and on your servers. If you switch it around and go to the microcontrollers, the difference it's certainly there. It's still running, a lot of them are running ARM CPUs, a little bit less clock less aggressively. Usually we see people running at the high end of the embedded space, Cortex M7 chips. Then the amount of RAM is quite limited here, so we probably see around maybe 300K on a very good day. But maybe the biggest difference is really that a lot of these chips do not come with a lot of fancy memory management support. So that means that they cannot really run any of the regular OSs in any meaningful way. Even micro Linux from a stack based on C. So what we do is at the bottom layer we have a traditional embedded real-time OS. We use FreeRTOS for a lot of things because it's open and available, and we like this sort of accessibility that's built into that. On top of that, we put the Dartino runtime, and then we actually allow you to have multiple independently developed programs that run on top of this setup. This is very different from a lot of the systems that run straight on the embedded real-time OS, because they don't really have a way of running sort of independent components in a truly independent way, because they also interfere and needs to be linked together in one sort of ELF file at the end of the day, or one binary file that can be flashed. So this is an area where having a abstraction layer in form of a runtime, a virtual machine you could say, really adds some value that you can get from a runtime instead of having that from a traditional OS based on systems that have memory management support that allows this. On top of these multiple programs, we actually do run multiple processes, so you can have multiple sort of independently executing versions of the program or parts of the program running next to each other. It's very much inspired by some of the success with Erlang, where being able to sort of model your concurrency in a very straightforward way by splitting it up into multiple independently executing processes seems to be a good way to get some more fault. UC Linux, which is sort of scaled down, not using the MMU and everything, still takes up too much RAM to run in these devices. So it doesn't really fit. So you're sort of stuck in a mode where you don't have an operating system, so you need to run sort of on the bare metal on these devices. This is our focus in the Dartino project. We want to try to make it a lot easier to write software for microcontrollers and maybe sort of bridge the gap a little bit so that some of the things you can do on microprocessor based devices is also possible in a microcontroller space. So I don't know how many people here are familiar with Dart. Show of hands. Oh, it's like a third of the people here know about what it is. So Dart is actually a fairly heavily used language at Google these days. It's mostly used to build web applications. Google AdWords is building the new version of their product in Dart. So it's sort of an unfamiliar territory to venture into to try to make Dart run really well on these small devices. The code is fairly familiar to people with an interest in languages based on curly braces. It looks like C, Java, C++, C#. There's certainly a lot of inspiration from those languages, and it's designed to look very familiar. And I think in many ways that worked pretty well. It also means that it sometimes comes across as a little bit of a boring language. It doesn't feel very novel. It doesn't feel very exciting at the syntax level, but there's a lot of good properties in the language also for making it run on these small devices that I'll try to go through. If you want to try it out in a browser, you can go to the Dartpad site and just play with the language a little bit there to get a feel for what it is. So why would you want to put something like Dart on a microcontroller? There are a number of reasons why. I think one of the most important things is that the number of developers in the world that are actually comfortable and productive writing software for these devices is very low. So it's very hard for people to actually to scale up and build good software for all these devices out there. So it's really important that we make these small platforms accessible to more developers. It's also, I think, important that that this area of software development for these small devices is certainly an area that's still lacking a lot of innovation. It has a very sort of old school feel to it. So I think it's important that we upgrade the development experience and make it much more modern and productive. And we need to turn some of the proprietary stacks into something that's more open and more flexible. So we have a possibility to actually get some innovation going in that space as well. Everything we do in the Dart and Dartino project is open source, and we're trying to seed some technology here and try to make it useful. So in a sense, I think we really need to extend the tool set that our people are used to building software for these small devices. GCC is already the biggest thing that people use in this space, plus a lot of sort of more hardware-near tools. I think we need to extend that a bit, and don't have like C code and GCC and GDB be the only options in these devices. It's a very, very scary place for people that just have a good business idea, they want to build some software for embedded devices to enter into, and a lot of people just cannot get it done at all. I used to think that the biggest problem was actually like doing the hardware side, but it seems like software on these small devices is a really big issue too. We talked to a lot of people that are building these small devices, and even in low quantity software, the software side of the cost of building new devices is sort of estimated to be maybe 2/3 of the overall thing. So that's certainly changed, right? Even if you look at a 500 to 1,000 quantities of custom hardware design, so which is somewhat surprising. I think that it's already getting there. So I think we need to do better than this, at least for the you could say the higher end of the low end embedded devices. We're specifically not targeting small 8-bit microcontrollers or anything like that. I think there are much better tools for that. But for these fairly spiffy new devices that come out, you can do better. So the programming model that we're proposing for a managed language on these small devices needs to be a little bit more flexible than what you can get from